Recording going now. Okay, it's running now. All right, our first presenter is Skip Bell. He's the Soil Survey Office leader for the Morgantown MLRA Soil Survey Office. And they've been working a lot in the high elevation areas of West Virginia and adjacent states in the what's considered the historic red spruce ecosystem, and I believe they're going to have some further explanation each of the presentations, or the presenters, I should say, and give you a little bit more background as they go. So I don't really want to hold Skip's presentation up much here, but we're going to be working through this. I think all the presenters, it's kind of new to them in terms of this the technology here we have set up for the webinar, and also going live as well. We've got it projected on the wall here, and hopefully everybody's got the full screen view of these presentations. Is that the case, Sean, that you can see?
Yes, and I just asked all the presenters to please speak up. Had a question, comment that it's hard to hear over the phone, so be sure to use your presentation voices.
Yeah, that's the pointer right there. Is the pointer working there, Sean? Okay, this won't get around. Use the pointer.
Right again?
Oh, I just asked if the pointer was working.
No, I'm not seeing it on the screen.
Good morning, everyone. I'm Skip Bell. Thank you, Dave, for that introduction. And I went through the title of this presentation went through several iterations. I now finally settled on rediscovering Spodosols in the Allegheny Highlands. And it is sort of a tale of rediscovery, but I'm not going to really go into why it's a rediscovery until the end of the talk. So let's start with a little recent history. Okay. Next slide's taking some time. There we go. All right, this whole project sort of got underway with the help of a couple of folks. Shane Jones, a biologist with the Forest Service out of the Bartow Ranger District there, Cheat Ranger District, and Jason Teets. Where's Jason? Here he comes. Here's Jason. Stephanie Conley asked Jason and Shane to collect some soils information and some data in the Upper Greenbrier River watershed for a NEPA document for the Upper Greenbrier River project. So they were up there looking at soils, looking at some flying squirrel habitat, and they started seeing some soil properties that had never been documented in the soil survey reports. They started seeing soils with very thick organic horizons. Some of them were thick enough to be classified as pholistic epipetons. And they also started seeing some evidence of podzolisation in some of these soils. I'm going to go into what podzolisation is in a little while. So these properties were not recognized in the current soil survey. So this was sort of what we thought was new stuff that we were looking at. So this is the area we were, it's a big picture of the project area. You see where it is in relationship to the MLRA 127 boundary. MLRA 127 is the eastern Allegheny Plateau and Mountains, and that's our office there in Morgantown. We maintain the soil database for that whole region. So that green area right there is the area that we were looking at. You zoom in a little closer, and this was the original. This is the Upper Greenbrier watershed. But we soon, the project spread into some other areas with very similar parent materials and landforms and climate in Randolph County and also into Highland County, Virginia, and Pendleton County. So we started looking at very similar soil mapping units in 4 different survey areas. And this is the current Surgo data. On the uplands, there's basically 3 different soil series that are currently correlated on these landforms. Burke's moist and DeKalb moist. Those were correlated in the soil survey of Randolph County, which was correlated in 1982. And Mandy map units were correlated in some newer surveys in Pocahontas County and Pendleton County and Highland County, Virginia. The Burks and the Cobb and Mandy are all belong to the soil order Insectosols. That means they're young soils. They do not show much evidence of soil development. So when you look at a profile of these soils, the horizons are not strongly expressed. They're young soils. When you look at the official series descriptions for these soils, they do not mention anything about pholistic epipetalons, nor do they mention anything about any evidence of podzolization. And here again are the map units that we're looking at in the different soil survey areas, and a look at the geologic parent materials. And these series were mapped on 3 different formations: the Chemung, the Hampshire, and the Price formation, which is used to be called the Pocono formation. All of these are acid bedrocks. The Chemung and Hampshire are dominantly shales with some sandstone members. The Pocono is dominantly a sandstone formation, although in our project area it also has shales and siltstones, and those seem to be dominant in the areas that we were looking at. And there's a look at the extent of those bedrocks. You can see it's about Chemung and Hampshire are the most extensive. There's really not much of the Price formation. It's about evenly split between the Chemung and the Hampshire formations. So let's go into, I want to go into some basic definitions. So as we go through this presentation, we'll all be on the same page. A Spodosol is one of the 12 soil orders. It's basically it's a forest soil. These soils form under forest canopy, and it's a mineral soil with a spodic horizon. A spodic horizon is a horizon in a soil profile that has an accumulation of translocated organic matter and oxides of aluminum with or without iron oxides. And podzolization is the process by which a spodic horizon forms. And it's basically a dissolution, a translocation, and precipitation are the 3 processes in podzolization. So we have to go into soil taxonomy a little bit so we can know what the criteria for a spodic horizon is. These are acid. You have to have an acid condition for the podzolization process to take place. So one of the criteria is a pH of 5.9 or less. Also, the aluminum and iron oxides extraction has to be, you have to have an accumulation, you have to show evidence of that these oxides were translocated. So you have to see a horizon that has less of those oxides in an overlying horizon than in the spodic horizon. So the horizon that overlays the spodic horizon should have fewer by weight aluminum and iron oxides. And there's a laboratory analysis called optical density of oxalate extract, and that's basically provides evidence of translocated organic matter. So we're going to take a look at a soil profile that's been podzolized. This is a Spodosol, and you get some to start this process. You get some organic acids that are released during the decomposition of forest litter.
Your pointer won't work if you hold the button down. People in the webinar can see it.
Okay.
Okay, yeah, thanks.
So you get some organic acids generated up in this organic horizon. These acids come down through the soil profile, and you get an area of intense weathering, and you get the dissolution of minerals and the release of iron and aluminum. And then the iron and aluminum are complexed with organic matter, and they're translocated down through the profile, where they precipitate. Well, that's the area of dissolution that leaves sort of a leached-looking layer, and that we call it, when we describe a soil profile, we call that an E horizon, E for eluvial, which is the process of translocation. And you get the precipitation, and which forms the spodic horizon. And when we describe these in the field, we describe these as a BS, a BHS, or a BH horizon. The S stands for sesquioxides. Those are the aluminum and iron oxides. The H stands for humus. So depending on the amount of the relative amount of organic matter, the spodic horizon could be described as three different horizon designations. So what environmental factors favor podzolization? So let's look at those and then see if we satisfy those in the area that we were investigating. You have to have a moist climate. And we do have a moist climate in an area we investigated. Most of that area has 50 plus inches of precipitation a year. Coniferous or heath vegetation favors podzolization. And our area of investigation is within the historic range of the red spruce forest, so we satisfy that factor. Acid parent materials. And our parent materials that form our soils are all weathered from acid shales and sandstones, so we satisfy that criteria. Coarse textured soils favor podzolization. But we really don't have that. Most of our soils are fairly fine textured in the fine earth, so that throws up a little bit of a caution. And I want to take a little closer look at the climate. This climate graph was generated using Newhall simulation model. Took the climate data from the Glady weather station and plugged it into the model. Glady is probably that's the closest weather station to the area we were investigating. And the blue area is precipitation, and the maroon area is potential evapotranspiration. And you can see that for every month of the year, precipitation exceeds potential evapotranspiration. So we do have a very moist climate. The soils are modeled to have a per unit moisture regime. In 2010, we started collecting field data, and we collected data during parts of 3 different field seasons from 2010 to 2012. We collected data at 330 sites, and that data included pedon descriptions and vegetation and site characteristics like slope and stone cover. And we also applied what we call the Spodic Intensity Index, which was developed by Tim Dillaplane, who's a soil scientist in our MLRA office. That's Tim there in the slide. And this index is based on soil morphology, and so it was a way to keep the describers consistent, so that when we looked at these soils in the field, we'd all be describing the same thing. So after we analyzed the data, we had two different soils that were dominant on the landscape. One of them had had good spodic development and had good Spodosol morphology, had well-expressed E horizons, a well-expressed spodic horizon. And we found these basically 26% of the pedons that we looked at had this type of morphology. There was not an established soil series for these soils, so we're proposing a new soil series. We named it Willdale, after the old logging town of Willdale on the west fork of the Greenbrier River. And Willdale is a Spodosol, and that's a photograph of the typical pedon for the new Willdale series. The other dominant soil type did fit within, morphologically, fit within the range for Mandy, but we described the BS horizon in these soils. They were very subtle. You had to sort of tune into these BS horizons. As Jason Teets said, you had to put on your Spodicles to see these in the field. But you did get a reddening. Usually the hue, you got one hue redder from the horizon above. Usually the BS horizons were a 7.5 YR hue. And you also usually saw some evidence of smeariness. So you could feel a little bit of smeariness in the BS horizons. And that was from these aluminum and iron accessory oxides that are non-crystalline minerals, and they give you a smeary manner of failure when you squeeze them with your fingers. So this was sort of it's an intergrade between a Spodosol and a Septosol. We're going to reclassify the Mandy series as from a typic distra depth to a spodic distra depth to recognize some of these spodic characteristics. In 2012, we started a sampling project, and we sampled 7 pedons. 3 pedons were sampled as members of the Willdale soil series, and 4 pedons were sampled as members of the Mandy soil series. That's Andrea and Nottingham. They're collecting some sample to determine the bulk density of an O horizon, an organic surface horizon. So I graphed some of the data, and these are the aluminum and iron oxides, and you can see, especially in the Willdale, you have your zone of dissolution, your leached layer at the top. This would be the E horizon. And then you get a nice curve here in your zone of accumulation, the spodic horizon. And then it drops off below the spodic horizon. And the Mandy, you get the same graph, but it's not as pronounced. It's not nearly as podzolized as the Willdale. I plotted carbon, and again, in the Willdale, you get a nice curve which shows you that there's been organic matter has been translocated down through the profile. In the Mandy, you don't get that curve at all. You just start off with a fairly high carbon level in the surface, where you have a lot of organic matter in an A horizon, then it just drops off very smoothly. So you don't have much evidence of translocation of organic matter in the Mandy, but you do in the Willdale. And this is the optical density oxalate extract values. Again, you get a nice curve in the Willdale, and no response in the Mandy. So this, again, this is the ODOE is an indicator of translocation of organic matter. So you can see we do have some translocation in the Willdale, but none in the Mandy. So how do these chemical properties, how do they relate to soil morphology? This is the carbon plotted on the soil profile for a Mandy soil. This is the soil that we sampled. So you can see this is a highly organic A horizon, and then it drops off very smoothly as you go down through the profile. Here's the aluminum and iron oxides plotted in the Mandy. And you can see right here, we get a little zone of eluviation, and then a zone of accumulation in the BS horizon, and then it drops off. And you can see that the BS horizon is a little bit redder than the horizon overlying it, and also the horizon below it. That redness comes from the iron oxides. Here's the Willdale series plotted with the carbon data. Again, you get the nice high carbon level. This is an organic surface horizon. It drops off dramatically in the E horizon. This bleached looking layer right there goes from 36 down to 2.5. And then it doubles in the spodic horizon. So you get a nice curve here showing that the organic matter has been translocated, and then it drops off below the spodic horizon. If we look at the aluminum and iron oxides, you get the same type of curve. Here you get the low values in the E horizon, and then they jump up dramatically in the spodic horizon and drop back off as you get below the spodic horizon into a BW and a BC and a C horizon. So these are the products that we're going to produce from all this data. We're going to update our Surgo data, and that's Surgo is our visual soils soil data. We'll update that data on approximately 100,000 acres. We'll have our map units. We'll have our major soil components will be populated with real data generated by the Kellogg Soil Survey Laboratory. Our soil components on our map units will be linked to ecological site descriptions. We're going to establish one new series, the Willdale series. There's its classification. And we're going to reclassify and refine the range and characteristics for the Mandy series. It was a typic district, and now it's going to be a spodic district, and I believe it's going to be the first member of that family. And we're also going to be correlating minor components in our map unit, our data map units. The minor components are a result of all the data that we collected. We can name those minor components, and so that will round out those data map units very well. Now, I'll get into why this is really a tale of rediscovery. This is a copy of the 1931 Soil Survey report for Randolph County. And this only came to light to us about 3 months ago. We found this soil survey stashed in a box in the back of my office. So I digitized we scanned the soil survey map, and the areas between these red lines in 1931, these were correlated as members of the Latonia soil series. Although back then, I'm not sure that they were really called series. They were just Latonia soils. And here's a profile description from the soil survey report. The classification of Latonia, in the old classification system, it was classified as a podzol, and those today are recognized as Spodosols. This is the current extent of the Latonia series. It's still being mapped, it's still being correlated. It's an active soil series. The concept of this series has been refined over the years so that it doesn't really fit the soils properties that we were seeing in the project area. It's now classified as a sandy skeletal enthic haplorthod. The sandy skeletal textural family means the fine earth textures are loamy sand, loamy fine sand, or sand. So this is a real sandy soil, not really what we were seeing. Most of our textures, fine earth textures, were silt loam, silty clay loam, and clay loam. So that's a profile of our Willdale, a typical pennant for our Willdale on the right, and on the left is the description of the Latonia stony loam from the 1931 Soil Survey report. So you can see that they were basically describing our Willdale soil in 1931. So there's the old mapping, the 1931 mapping, where they mapped the podzol. And this is our new Surgo layer. The green is our new mapping, where we're going to be mapping a complex of Willdale and Mandy. And both of these will now recognize spodic properties. Willdale being the spodosol, and Mandy being the inceptisol, spodosol integrated. So it's pretty close, isn't it? So I guess the lesson of this is that, like good people, good data does not lose its usefulness with age. It's still good data. And I'll take any questions. Anybody has any questions? Yes?
I have a question. This is just more not having that strong soil science background, but looking at the Mandy source, I guess I don't see that distinct difference when you guys tease down in the field. And so I'm just curious, are there other explanations for that evidence of concentration besides this one responsibility? Are there other, how confident are you on that?
On the Mandy?
Yeah, on that new classification.
I'm very confident with it. I mean, all the lab data we got back supports that classification. So I'm very confident in it.
If you repeat the question so that the folks can hear it well.
The question was how confident am I in the new classification of the Mandy soil, seeing that the morphology is not very strongly expressed, the spodic morphology. And my answer was I'm very confident because the laboratory data that came back does support that. Yes?
This might, I don't have a soil science background, so this may be a question, but can you talk a little bit about the process of depopulation, and does Sodosol, through the process of depopulation, become a spodic disturbance, or are they totally separate?
Okay, the question was, could I talk a little bit about deposilization, and does a Spodosol...
Yes, in the process of depopulation, I guess I'm trying to figure out where the two fit together.
Right.
How do you, I'm sorry, I don't have a question.
So that's a good question. So your question is, does the process of deposilization turn a Spodosol into a spodic dystrodon? And I think the answer is yes. I think Travis is going to talk a lot more about that this afternoon, so I don't want to go too deeply into that because I really don't have that much knowledge of it, but I think Travis does. But in my opinion, yes, I think it does.
Yes, this is Sean, and we have some
Yeah.
online questions.
Okay.
Question, why frigid and not mesic?
Well, we do have soil temperature data. The temperature regime, I mean, it's right at the mesic frigid boundary. Depending on what elevation you're at, the mean annual soil temperature is anywhere from maybe 7.5 to 8.5. So we just think it's better to classify these soils as frigid than it is mesic. I just think interpretively they interpret more like a frigid soil than a mesic soil.
And then there's a follow-up question here online, and kind of a technical question. What are the field color criteria for the spodic horizon?
Well, they have to be a hue 7.5 YR or redder. And off the top of my head, I cannot think of what the values in chromas for a BS horizon versus a BH horizon is. A BH horizon, of course, it's got a lower value, lower chroma, but I think it has to be a 3.3 for a BH, and a BS can be a 3.3 or less chroma and value. A BS, I think it has to be a chroma of 6 or less and a value of 5 or less, I believe. I know it has to be a hue 7.5 YR or redder. And all of our spodic horizons met that criteria. Any other questions? All right.
You don't have any more, Sean?
No, there's no more online questions.
All right. Thank you very much.
Okay, so we are going to stick with the agenda schedule because so people can join in to the webinars at the scheduled time according to the agenda. So for right now, we're going to take a break. Here in Canadian Valley Institute, we have coffee and baked goods in the back for our morning break. And our next speaker talking will be Jason Keats, using ESDs to describe and manage the habitat of West Virginia northern flying squirrel in West Virginia. And if you haven't realized, this technical seminar is going to start to tell a story. And we're starting with the ground, and we're going to move up, and we're going to end our day with a facilitated question and answer session about, so what does this mean for land managers? You know, where are we going with all this new information, and how are we going to utilize it in the future in the face of climate change, in the face of landscape resiliency, and the questions about restoration and water quality? How can we use this information to be better planners, better managers? Okay, thank you. So we will start back up again at 10:45 promptly.
Okay, Sean, we're going to stop the recording now. And we're going to leave this on. We'll probably put you on mute, Sean, since we're going to be still dialed in. Is that okay?
Yeah, that's fine.
Okay, and I'll try to, I'll unmute it a couple minutes before.
And we've got some, text here that sounds like it's not.
Perfect, yeah, that's
All right,
perfect.
yeah.
There you go.
I have a question. So if we turn the volume down,